Why, hello, world. It's me, Mr. DeRozier. Some of the students who have been watching the videos have said we're wondering what the space that you're working in looks like. Well, welcome to my study. There's all sorts of pictures in the background of my wife, of my two daughters. I'm a big fan of Superman stuff. You see that up here. I'm a big fan of Doctor Who and Einstein. You're going to see them up there. We even have Kermit the Frog in the corner and a TARDIS. All sorts of fun stuff, fun toys, and of course, a bookshelf filled with calculus books. Wouldn't have it any other way. Anyway, enough about that. Let's get back to the calculus, shall we? Okay, so tonight's topic is implicit differentiation. And this is something that we did a long time ago. This was back in Unit 4. If you're wondering where this is in the special topics packet, it was sort of awkwardly placed a little bit of the ways down on page 26. But let's just do a quick recap. When we first started the course, everything we did was explicit. We looked at functions like y equals x squared plus sine of 2x. And when you were explicit meant you had y, the equation was already set up in like y equals form or f of x is equal to form. It was explicit. Your dependent variable was expressed in terms of the independent variable. And so when you were asked to find a derivative, well, you would take the derivative on the right and say, well, what's the derivative of x squared? Well, that's 2x. Plus, what's the derivative of sine 2x? Well, that's going to be the cosine of 2x times 2 because of the chain rule. But what do you write on the left? You write down the derivative of y, which isn't 1. You would write it's dy dx. This is a measure of how y is changing with respect to x. So we want to be really careful there. We did it, but we almost did it automatically. The derivative of x with respect to x is 1, but the derivative with respect to x of something like y is dy dx. It's this idea from explicit differentiation that we're going to need, and we're going to need a lot with implicit differentiation. Because what you're going to see in this first problem, we have x times y squared minus x cubed y is equal to 6. And what we want to do is we want to find dy dx. We want to find the derivative of y with respect to x. Now, some teachers are going to tell their students that what they have to do is solve this equation for y. And whether we can or we can't, I'm not even going to bother trying that. I'm just going to find the derivative just like we did in explicitly defined curves. But I'm going to find the derivative of each term, and I'm going to do it very carefully. We need to find the derivative of xy squared, minus we need the derivative of x cubed y, and that's going to be equal to the derivative of 6. Now, I know you might be thinking, but wait, I know the derivative of 6 is 0. Good, I'm glad you do. But let's take a bit here. How am I going to find the derivative of x times y squared? Well, x times y squared is a product rule. So the derivative of x times y squared, the product rule says take the derivative of the first term, which is 1, leave the second one alone, plus now you leave the first term alone, and you multiply by the derivative of y squared. Well, we're taking the derivative with respect to x of y squared. You need to use the chain rule. This will be 2y dy dx. The derivative of y squared is 2y, but I'm taking the derivative of y with respect to x. Hence, I have the dy dx. This comes from the chain rule. Minus, I need the derivative of x cubed times y. Well, x cubed times y is another product rule. The derivative of x cubed is 3x squared. Leave the second term alone. Plus the first term times the derivative of y, which is dy dx. And that's going to be equal to the derivative of 6, which is 0. Sorry, poor planning on my part. To To find dy dx, we're going to have to do a little bit of algebra trickery here. So let me multiply this out. I've got y squared plus 2xy dy dx. I'm going to distribute the negative through, minus 3x squared y minus x cubed dy dx. I want to solve for dy dx. I see that I have a dy dx over here, and I have a dy dx over here. The algebra says keep the terms that involve a dy dx on one side and move the terms that don't have the dy dx to the other side. Well, let's look at that. 2xy times dy dx minus x cubed times dy dx is equal to, move the y squared to the other side, now it becomes a negative. Move the negative 3x squared y to the other side, now it becomes a positive. The reason that we're going to do this moving things around is that now on the left side of the equation, both terms involve a dy dx. So I'm going to factor out the dy dx, and that leaves me 2xy minus x cubed equals negative y squared plus 3x squared y. Finally, to solve for dy dx, we're going to divide both sides by this expression, and we're going to get negative y squared plus 3x squared y over 2xy minus x cubed. This guy here is your final answer. This is the derivative of y with respect to x. What's different is that you now have a derivative that involves both x's and y. That's a little more complicated, it's a little trickier, but we can absolutely do this. It's just a matter of getting comfortable with the process, recognizing things like, I need a product rule here, recognizing that when you take the derivative of something that involves a y, you're applying the chain rule, and then a little bit of algebra at the end. Okay, let's keep going. Okay, so this is at the bottom of page 26. You're going to see prompts like this, and I just want to make sure that we're all on the same page of what to do. If I want to determine where the tangent line is horizontal for an expression like this, well, what does that mean? If your derivative, if you have a horizontal tangent line means that dy dx is equal to 0. If I have an expression like this one, well, why would dy dx be equal to 0? That's when your numerator, the top part of the fraction, is equal to 0. But the denominator is not equal to 0. So I want to be very specific here. And if we're dealing with a fraction, the numerator is equal to 0, but your denominator cannot be equal to 0. If I ask the question about a place where the tangent line is vertical, well, now that means that dy dx is undefined. And if your derivative is undefined, now it's a switch. The denominator is equal to 0. I'm trying to divide by 0. That's why my derivative is undefined. But the numerator is not equal to 0. Yes. Okay, if I want to find d squared y dx squared in terms of x and y, what this means is d squared y dx squared. You guys know that. That's your second derivative. Okay, clearly I need to get rid of this pen. That's the second derivative, so you're going to find the derivative with respect to x of whatever your first derivative is. Now, in a problem like this one, I know I'm doing a lot of back and forth here. If I asked you to find the derivative of this expression, yes, that would be ugly, but you would have to use, because I see a fraction here, a quotient rule. We're going to do low, d high, minus high, d low, all over low, low. When you take the derivative of something like y squared with respect to x, you're doing implicit differentiation again. You're going to get another dy dx expression. Okay, let's keep going. If I asked you to find the equation of the tangent line, well, you're going to say L of x is your slope. Where does that slope come from? It's going to be the value of dy dx at this particular point. So I'll say at the point x1 comma y1, and then it's x minus x1 plus y1. And if you were told that dy dx is equal to 0 at a given point, and you needed to determine whether the curve has a maximum or a minimum, well, if dy dx is equal to 0, what that means is you have a horizontal tangent line. Horizontal tangent line doesn't mean anything other than your graph is flat. If you have a relative maximum, and you know you have a horizontal tangent line, for a relative max, what you're going to do is you're actually going to look at the second derivative, d squared y dx squared. If your second derivative is negative, then you have a relative max. If you have a relative minimum, that looks like this guy here, for a relative minimum, that's going to occur if your second derivative is positive. Your graph is concave up. Okay, so that was just a summary of some things I want you to keep in mind when we're working with implicit differentiation. And now let's all flip over to page 28, where we're actually going to work through a free response question involving implicit differentiation. Now, back in the day when I was in calculus in high school, implicit differentiation was almost on every single AP exam. It's less frequently tested now on the free response. Occasionally shows up on the multiple choice, but I really like this topic because you get a chance to practice your derivative skills, you get a chance to practice your functional analysis skills. There's just a lot of good math going on here. Okay, so this was on the 2005 AP exam, question number 5, calculator inactive. And I'd say this is a pretty typical question with a couple of tricky parts thrown in. Consider the curve given by y squared equals 2 plus xy. I want to show that the derivative is equal to y over 2y minus x. Now, stop and think for a second. They gave you the curve and they gave you the derivative. All you have to do is find the derivative and show that it's actually equal to this guy over here. Well, let's do it. What's the derivative of y squared? 2y times dy dx equals the derivative of 2, that's 0, plus the derivative of xy. I'm actually going to write that. I really like doing this. I'm just going to say write it as derivative of xy. I'm not done yet. Why am I not done? I never found the derivative here. How am I going to find the derivative of xy? This is really x times y. This is a product rule. So 2y times dy dx. Product rule says derivative of the first, which is 1. Leave the second part alone. Plus the first times the derivative of the second. The derivative of y with respect to x is dy dx. My goal is to show dy dx equals this expression over here. So what I'm going to do is I'm going to solve for dy dx. What we did last time, terms that had dy dx, move them onto the same side. So I'm going to say 2y times dy dx minus x times dy dx. I took care of this term. I moved that term to the other side. That's equal to y. Again, you move the terms that have a dy dx to the same side so you can factor out the dy dx. dy dx times 2y minus x equals y. Solve for dy dx through a division move here. Y equals 2y minus x. What did the College Board do? I think they said getting here, correctly finding the derivative of all the terms was worth 1 point. Solving for dy dx was worth your second point for a grand total of 2 points. And another marker bites the dust. Man, we're just burning through all the markers tonight. Okay. Find all points x comma y on the curve where the line tangent to the curve has slope 1/2. Okay, think about that for a second. The line tangent to the curve, what is that? That's your tangent line. What they're saying is that dy dx is equal to 1/2. dy dx is equal to 1/2, but we also know that dy dx is equal to y over 2y minus x. What they're looking for are points where the expression y over 2y minus x is equal to 1/2. Now, at first you might think, wait a second, coach. I've got one equation, I've got x's and y's in here together. How could I possibly solve this? Well, how about if you do a little cross multiplication step? You get y times 2, 2y, equals 2y minus x times 1. If 2y equals 2y minus x, I can subtract 2y from both sides. You get that 0 equals negative x, or x is equal to 0. Now, for the calculus teachers out there, I want to be really careful because I think the solutions are incorrect. I'm looking for points that are of the form x comma y. So what I know is that the x coordinate is 0, but we haven't figured out the y coordinate. In order to figure that out, you know the x. How do you figure out the y? You go back to your original expression. You go back to this y squared equals 2 plus xy, and let x equal 0. Y squared equals 2 plus 0 times y. That means that y squared is equal to 2. So y is plus or minus the square root of 2, meaning there's actually 2 points to consider. The points are 0 square root of 2 and 0 negative square root of 2. And let's see, what did I see on the scoring rubric? 1 point for knowing to set the derivative expression equal to 1/2. 1 point for solving and getting x equals 0. Kaylin, time's up. And then 1 more point for finding the y values, but you have to write the points as coordinates x comma y and x comma y. So this is 3 points. You're out of TV time. Sorry about that. I needed to pause and go take care of the tiny humans in my life. Okay. All right, part C. This one's tricky. Show that there are no points on the curve where the line tangent to the curve is horizontal. Wait a minute. In part B, we wanted to find places where the tangent line had a slope of 1/2. In part C, we want to show that there are no points where the line tangent to the curve is horizontal. So what they're saying is dy dx is never going to be equal to 0. The way that we're going to solve a problem like this is called proof by contradiction. What we're going to do is we're going to assume that there is some place where dy dx, which is this y over 2y minus x, is equal to 0. We're going to assume that this is true. Well, what would have to happen for y over 2y minus x to be equal to 0? If this fraction is equal to 0, then it means that y is equal to 0. Okay, I don't see a problem. But if y is equal to 0, use that in the initial equation. That would tell me that 0 squared equals 2 plus x times 0, or that 0 is equal to 2. 0 can never be equal to 2, which means that y cannot be equal to 0, which means that there is no place where the tangent line is horizontal. That's proof by contradiction. So I'd say, so the tangent line is never horizontal. Now, I can't remember exactly how they awarded points. What I know is that this was a 2-point question. I've only seen them ask a question like this one time. My assumption is most students, when they took the test, had no idea what to do, and the College Board said, okay, let's not do that again. But let's look at part D, and then we'll close it out. Let x and y be functions of time related by the equation y squared equals 2 plus xy. At time t equals 5, the value of y is 3, and dy dt, the derivative of y with respect to t, is 6. Find the value of dx dt at t equals 5. Okay, we got a whole lot going on here. We know that y squared equals 2 plus x times y. So for any point on the curve, I'm going to satisfy this equation. At t equals 5, at this moment in time, what do we know? We know that the y value is 3. We know that dy dt is equal to 6. What we don't know is dx dt. That's what we're after. Well, dy dt, dx dt, these are derivatives with respect to t. What we've been doing all throughout this problem is finding derivatives with respect to x. When you take the derivative with respect to t, it kind of works the same way as implicit differentiation, which is why they put these ideas together. What's the derivative of y squared with respect to t? Well, that's 2y times dy dt. You were probably thinking I was going to write dy dx here. This is 2y times dy dt because we're measuring how y changes with respect to time. That's going to be equal to the derivative of 2, which is 0, plus the derivative with respect to time of xy. And I wrote it out this way because, again, we need a product rule. 2y times dy dt. The derivative of xy with respect to t will be derivative of the first, dx dt, times the second, plus the first, times the derivative of the second. What I want is dx dt. I want this guy here at t equals 5. Okay, well, what do we know? We know at time t equals 5, we know that y is 3, so I have 2 times 3 times dy dt is 6, is equal to dx dt, that's the part I don't know, times y, which is 3, plus x, oh, I don't know x, times dy dt, which is equal to 6. What I want is dx dt. The problem is we haven't figured out what x is, but here's the good news. What do we know? We know that for all points on the curve, y squared equals 2 plus x times y. We know that y is equal to 3. Using that, we can figure out x. 3 squared equals 2 plus x times 3. That means 9 equals 2 plus 3x. Solving, we get that x is 7 over 3. I'm going to take that and plug that in over here. So what do we have? I have 2 times 3 times 6, that's 36. dx dt times 3 is 3 times dx dt, plus 7 over 3 times 6. 7 thirds times 6 is 14. 36 equals 3 times dx dt, plus 14. A little bit of quick math here. Subtract 14 from both sides. Divide both sides by 3. dx dt is 22 over 3. And that's your final answer. I think what they did is they awarded 1 point for correctly finding the derivative with respect to t. They then awarded 1 point for figuring out the x value at t equals 5, and then 1 final point for dx dt. Now, I didn't look up the scoring rubric, so I could be wrong here. I think I'm wrong because if part D is 3 points, if I'm correct on all the other things, this would be a total of 10 points. The College Board free response is always worth 9 points. Regardless of the scoring rubric, though, these are typical implicit differentiation questions that you could expect to see on the free response. So I'm going to call it a night, post this, and I'll see you all tomorrow.